video, I will be showing you how you can implement a physics-informed neural network in Python in order to solve differential equations or a specific class of differential equations which are going to be non-linear partial differential equations. So, if you don't know what a pin is, we're going to be covering that. We're going to look at briefly as what a pin is and how it works. And this is going to be a paper implementation video, so we are not actually going to be uh, like we are not going to be looking up at various sources and things like that. We're going to be reading the paper and then we're going to be looking at the implementation of the pin. Now, I have actually gone ahead and done this entire implementation by myself. So I have the code over here on GitHub if you guys want to go ahead and check it out. Uh, I'll have the link to this repository in the video description so you guys can go ahead and check it out. It is not perfect. There are a couple of stupid errors that I've made, like I haven't actually put my thing onto the device and things like that. Like there are a bunch of errors, but uh, you know, overall it works, and like in terms of the actual logic it's correct and you're gonna get a result. So yeah, that's that. So this is the code which we are gonna actually I'm gonna be walking you through. As you can see, this, as I said, it is a paper implementation. The goal of this video is not going to be to achieve perfection. Rather, it is going to be to give you a proof of concept that you can kind of build on. Like you can literally look at the pin network and you can see that the pin network class, like you can see that this is a very simple network. Like there is literally barely anything in this network. So yeah, that's that. You can see it's just 120 lines of code, not a lot, very simple stuff. So first off, what is a pin? How does it work? So we're gonna set the code aside for a while, and we're gonna first look at the theory. I wanna keep this video kind of implementation heavy and not theory heavy, majorly because I feel like there's a lot of really good content out for pins, and by some really good YouTubers who know what they're doing, like in terms of the math. And so I'm gonna go ahead and keep let those people handle the theory, and we can handle the implementation over here, because this is something that I'm a little bit more comfortable with. So yeah, so first off, the equation that we are choosing is the one-dimensional heat equation using Dirichlet boundary conditions and a sine function as the initial condition. If you don't know what this means, basically there's this equation known as the heat equation, which is used to model heat flow and like a temperature distribution or over some kind of a body. It's 1D, meaning it can model a temperature distribution over some kind of a one-dimensional line, and it's a function of two things. That means it's the function of the x and the function of time. And then the Dirichlet boundary conditions basically means that the temperature is going to be 0 at the x equals 0 and x equals L, where L is the length of the rod for any given time t. And then a sine function as the initial condition means that at time equals 0, for x equals 0 to x equals L, the function is going to be somewhat similar to a sine wave. So yeah, that's it for her actually piecing apart exactly what I have implemented. So this is the example that I've implemented. The people in the paper, they actually implemented a different example. They implemented the Burger's equation. The reason why I didn't implement that is because I didn't know exactly what I don't know what the Burger's equation is, and so I figured I won't do it. So this, as you can see, is the paper, and as you can see, I've gone ahead and done highlighting in order to give you guys a better understanding. Also, I did it because I did that when I was reading the paper myself, and this was a complete paper implementation. Like I used a little bit of Google search, like in order to actually correct some errors, and I used a little bit of GPT in order to just make sure that I was doing stuff correctly. But it was a paper implementation. So first off, what is a physics-informed neural network? So physics-informed neural networks are used to solve supervised tasks while respecting any given law of physics described by the general nonlinear partial differential equations. Basically what that means is that a physics-informed neural network is supervised. That's the first thing. Second thing is that it solves general nonlinear partial differential equations, but it also respects the fact that there are certain conditions in physics that you need to conserve. So a good example can be your boundary condition and your initial condition. For boundary valued problems and initial valued problems, those particular conditions need to be respected. furthermore, there can be other conditions, like let's say you look at the law of conservation of energy. Well, that particular law has to be respected if you're trying to solve some differential equation that has energy. Another thing is that energy has to be positive. That is another thing that has to be respected. So that's why pins are such so good, is because they are able to solve the equation and respect the fact that these particular things have to be fulfilled. So yeah, the next thing is, now this the particular paper that I've implemented is the physics informed deep learning part 1. I haven't actually implemented the part 2 yet. I don't know if I am going to do that, but basically part 1 is all about actually solving differential equations, and then part 2 is about actually discovering differential equations. I'm not doing that, I'm just doing the data driven solution. So depending on the nature and arrangement of available data, we have two different distinct class of algorithms, namely continuous time models and discrete time models. I am solving the continuous time version, and alright, so that's that. So I'm not gonna go through all of this because that's really just they are kind of building up why we need this, and what we already have right now, and I don't really want to read that. You guys can obviously go through with this. Uh, uh, I'll have maybe the link to the paper also in the description box down below. It's by Raisi et al. Uh, so yeah. So in this work, we take a different approach by employing deep neural networks and leverage their well-known capability as universal function approximators. Now, I know sometimes papers do get a little technical with their language, but basically what this word universal function approximator means is that neural networks, well, if you have studied neural networks and how they kind of work and how the backward pass works and how activation functions work, you will understand that at its heart, the way neural networks work is that you try to create a function which tries to estimate a data distribution, which means that neural networks are really universal function approximators, that no matter what dimensionality you are looking at, and no matter what kind of a function you are looking at, a neural network can theoretically estimate that or approximate that. In this setting, we can directly tackle nonlinear problems without the need for committing to any prior assumptions, linearization, or local time stepping. We exploit blah 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 blah. So basically, one very important thing is that they use automatic differentiation in order to do this. This is very very important, and it is pretty much the core of this entire paper. It's actually covered in this particular function, which we'll get to in some time. But yeah, so basically, automatic differentiation is this method in which you take a computation. So let's say I take the forward pass computation, and then I split it up into these sets of different operations and variables in this graph, in this computation graph. And then you basically step through each of the nodes in that graph, and you calculate the derivatives in a very that kind of a manner, like the backward pass kind of a manner. And basically, that is automatic differentiation. It is a very very powerful thing when you do it computationally, and that's kind of something that Pinch sort of try to exploit, because yeah. So one, all right, but okay. So the general aim of this work is to say, okay, yeah, to this end, let us consider the parameterized and non-linear partial differential equations of the general form of this. So I know this is a little bit hard to understand, but basically the ut of x is actually the solution that you want to develop from this, and operator parameterized by lambda. Now I feel like this is a little bit hard to understand of an equation, so we can actually go down and look at the example. So this setup encapsulates a wide range of problems in mathematical physics: conservation laws, diffusion processes, something. And as a motivating example, the one-dimensional Borger's equation corresponds to this, where this. Now, what exactly do this mean? So the u sub x actually stands for the partial derivative of u with respect to x, and the u sub xx means that it's the second partial derivative of u with respect to x squared. But yeah, I guess actually no x. So here the subscript denote partial differentiation in either time or space. So you can understand that the n term actually kind of means something like this. Given noisy measurements of the system, we are interested in finding the solution to two distinct problems. So in the first part of our two-part blah, this is what we want to solve, and pretty much yeah. So this is the where all of the important things starts, the continuous time models. So this particular thing that you can see over here, this the f is the definition of the physics and from neural network ft of x in this case, because we are solving it in a one-dimensional case. So by proceeding to approximate ut of x by a deep neural network, the assumption along with the equation 2 results in a physics-informed neural network. This network can be derived by applying the chain rule by differentiating the compositions of functions using automatic differentiation. Now you can look at this. This is the Burger's equation. Now you can see what they have done is they have kind of taken the LHS and the RHS and have put everything to one side. So that is something that even we have to do. And then you can look at this is the domain and for the x and the t. So we're going to be using the similar domains. So we're going to be using t from 0 to 1 and x from 0 to 1. And then you can see that these are the Dirichlet boundary conditions. So these are the boundary conditions we are not going to use. So these are sort of the boundary conditions we're going to be using. Other than that, you can see that they have really written this paper very readably. So this is a very good beginner paper to implement because they have actually provided snippets of code as to what they want you to do. So here, as you can see, they have just said that it's very simple. All you do is a ut of x function where you actually compute the u by applying the neural net to a concatenation of the weights and the biases to the t and x. We don't need to do that since we are using torch. And then you actually create your ft of x, which is your pin, wherein you actually compute the gradients and you actually implement this equation. And then they talk about the loss function. So the loss function is actually probably the hardest part to implement for this whole thing. Basically, it's a little lengthy, but the way you do it is uh, for boundary valued and initial valued problems, the loss function will have 4 parts. The first part is going to be the loss function at the boundary values. So the boundary values have to be 0. So basically, you have a mean squared error where you are comparing what outputs you get to some array of zeros. So you have to do that for the boundary conditions. Then you have the initial condition wherein you have, you're going to be comparing it to the initial conditions values. And then you're going to have the collocation points, which is going to be MSE of f, which is something written over here. So this is the loss function for the boundary values and the initial values. And then MSE of f is basically the loss function for all the collocation points, or all the points between the boundary values and after the initial value. So that's kind of all that they are trying to do. I really want to dive right into the implementation because I know that this is a little bit too theory heavy, and as I said, there are really good resources out there which kind of go through this entire thing really nicely. So I don't exactly want to do it all again because there are other resources. So we are going to be using Torch in order to do the implementation for this. Now usually I do recommend that people do their implementation in a Google Colab, and that is exactly what I've actually gone ahead and done. I simply open up Google Chrome. I've done the entire implementation first in a Google Colab, and as and when I finish the implementation, I end up copy pasting it into this local file. So yeah. Now, if you have any concerns regarding your computer not being fast enough, don't worry. For the particular model that we have trained, believe me, you can literally run this in a couple of seconds, max to max a minute, even on an i3. So believe me, you have no issues. So first thing is I define the number of steps. So number of steps is basically, well, we're going to be creating our own data set, right? Because you can't exactly search for heat equation solutions and have some large CSV file. We can just create our own data set. So the first thing is we need to create the collocation points. So what we do is we just create a torch length space from 0 to 1. Since, remember, throw back to the paper, we were defining t from 0 to 1. So we start at 0, end at 1, and we have these many steps. Now keep in mind, you have to set requires grad to true since we're going to be doing the backward pass. So if you want this to be in the computation graph, you need to tell Torch that, we will be doing some sort of a gradient computation on this, and so I want this to be in the computation graph. So always set requires grad to true for this particular case. So I set t and x, and then boundary conditions for the time. So for the boundary conditions for the time, I don't even know why I did it. It's literally the same thing. You start at 0, you end at 1, you have these many steps, requires grad is true. This is redundant code, I don't need that. And then left and right boundary conditions. In this case, I'm using torch.ones. I'll get to that. So for the left boundary condition, well, the left boundary condition is at x equals at x equals 0 and time t, the u of 0 comma t should be equal to 0. So I just say that x0 is just going to be a torch.zeros for these many steps, again requires grad should be true. And at x equals L, well, in this case L is 1, so I just do torch.ones and steps and requires grad as true. Not too crazy, right? Next, I just said u of 0, which is the initial condition ground truth. So this is the initial condition for my equation, which is just a 7 sine pi x over L. But here I haven't done the over L again because it's just 1. So it's just a 7 sine pi x. This is actually a very commonly used initial condition when solving the heat equation. So that's why I've just kind of rolled with that. And then I have the initial condition time. So all of the initial condition is going to be a u of x comma 0, right? So it's going to be, what is the condition of the x at time step equals 0? It's going to be the 7 sine pi x. So I just create an array of zeros, torch.0 steps requires grad equals true. So that is all for actually creating the data set. So now we are gonna have a bunch of points that we can work with. The next thing we can do is we can immediately jump into actually creating the neural network. Now really you don't have to spend a lot of time thinking about how you're gonna make this. It's a little bit simple to make. So first off, you need to consider actually the inputs. How many inputs does your neural network need to have? Well, that just corresponds to exactly how many inputs your function has. Now for the heat equation, your function has two inputs, which is your x and your t. So that's why my linear layer has two inputs, which is going to be x and t. And then I'm just having 200 neurons in there. And then I'm having the tanh activation function. Then I'm having 100 neurons in the second layer, tanh 100 to 1. Why 1 though? You have to ask that, believe me, because this 1 isn't something that remains constant. It changes equation to equation, so you need to understand why there's this 1. Basically, the output is going to be the number of values that your equation outputs. In our case, we are going to be outputting u of x comma t. So we are just outputting one value, and since we are outputting one value, the output has to be 1. And then I just do a forward on zel.net x, very simple stuff. This I've literally just copy pasted it from the paper. If you can just check it out over here, I've literally just gone ahead and copy pasted it from the paper. I've not even actually I've just translated the code from TensorFlow to Torch. I've literally not even done anything else. I'm just implementing the thing on that. As you can see, very simple stuff. For the other thing also, I've literally just gone ahead and copy pasted it from the paper. I've done a little bit of stuff. So you can see for the first thing I've done this. Basically what this is that the outputs of the neural network, what was happening is we were getting a 500 by 1 as an output, as the output array. And so when I was doing the backward pass on that, Torch was kind of not being able to process it since there was that extra dimension. So I just kind of removed that extra dimension by writing this. I not removed it, more like I just ignored that dimension and just got the 500 values. The next thing is this, which is probably going to be the meat of the code in terms of the computation, which is del u by del t. And the way you do it is you just do torch.autograd.grad, you take the O, pretty obvious stuff, and you differentiate it with respect to t. The next thing is grad output. So basically you want to have some sort of how do you exactly want to present the outputs of your networks, of your autograd. So basically you're calculating the gradients, but then you want what kind of a array or what shape of a tensor do you want in order to actually project these outputs. Well, then you just pass in this, and then you just say create graph equals true, and then you extract the 0th element because there's some sort of like there are 2 elements in there, or there's something like that. So you just extract the 0th element. Then for u of x, del u by del x, you just literally do the same thing. And then for this one, you actually do it with respect to u of x, since this is going to be the second derivative. Simple stuff, right? And then you just put everything to one side and you can solve the equation. And like you end up with your f, which is going to be some part of your collocation point. And that's literally it. Now we can actually start out with like the training loop kind of code. You define the loss, which is going to be a mean squared error, optimizer, epochs, and like I'm just kind of logging all of my losses in this list. I am just looping over the epochs, zeroing the grad, simple stuff. So here I'm actually doing the loss calculations. You can see it's a little bit, but it's, believe me, it's actually not that hard. It just looks a little bit more, but it's not too crazy. First thing is you at the left boundary condition and the right boundary condition. You can see I actually labeled the variables decently enough so you can understand that I'm currently evaluating this at the left boundary conditions, and then this is the left boundary condition loss, right boundary condition, and right boundary condition loss. Nothing too crazy, right? Like it's all relatively simple right now. It's not too difficult to kind of process and understand. Initial condition, evaluated at the initial condition, you apply the loss, and you just add everything up together. Again, nothing too crazy, something that everyone can understand, and very simple stuff. Next, we are going to be calculating the MSEF by validating it on the collocation points. Again, nothing else. You just do colloc points, ft x alpha equals 1, and then you just do torch.mean, colloc points squared. Why am I doing that? Because that is the equation right here. Yeah, sure, you can take the absolute value, but that's all right. But because since we are already getting, we are just, if you don't know, basically the function is only outputting positive values, so it doesn't really matter. You don't need the absolute in this case. Then I'm just adding up both the losses again, literally as it is shown in the paper. MSEU plus MSEF equals total loss, appending it and printing it out, backwarding it. Retain graph equals true. You need to do that basically because since you are calling the f function over here, uh, if you do a backward pass, basically what happens is that at backward, I think there's some sort of a deletion of things and deletion of nodes and stuff like that from torch, and so you can't actually do the backward since you have already taken those derivatives, and so there's a big problem regarding that. I don't know exactly what the problem is, but if you don't pass retain graph equals true, you're gonna get a problem. You're gonna get an error, but the error message is pretty good because they literally just stated out loud like you need to add retain graph equals true in your backward pass of the loss function. So yeah, now one disclaimer that I kind of like to always I want to give out: if you are doing this on a Google Collaboratory, if you are actually passing retain graph equals true, what ends up happening is that these notebooks, they end up caching your stuff. Every single output that you have and all the intermediate calculations, they all get cached. So basically, if you end up executing all of this code and all of this is going to be segregated in these other code cells, what's going to end up happening is if you go sequentially and then you end up, let's say, revisiting and executing some other upper line of code, and then you end up executing the training loop, you're going to get an error. You're going to keep on getting that error. After you write the training loop, you have to go right back from to the start of the code and execute everything in line. Only then you're going to have a cache that's going to contain everything that you want, and it's not going to have any mismatches and graph inaccuracies. So you wanna, so that's why what I did was I did the final training on my machine itself. I didn't do it on a Google, like I think I did it maybe. So I did it, but I only did like a very simple test on it. I didn't actually do the whole thing. So yeah, so I actually was stuck on that stupid little issue because I didn't realize the fact that my, since it's a notebook, it does the caching, and I was literally stuck on that issue for a day, and then I realized that that was my issue and that I wasn't actually doing anything wrong. It's just that uh, it was the way these notebooks worked. So that kind of sucked, but all right. Next, I'm just visualizing the losses. I'll just show you what the visualization of the losses look like so you have a decent understanding of. This graph is actually kind of important. I'll get to it in a second. So you can see that we start from like a 25 and then we go down to something like 8.5. Now the thing is, uh, pins are actually currently an active area of research in neural networks. These aren't thoroughly researched concepts that kind of just exist. These are currently in research. They are under research. I don't know exactly what preposition goes in there, but they are under research. Basically, there are a lot of things regarding conversions of pins that is a problem, and we can kind of see that problem in action right now. We can see that there was that little bump in the loss, and overall, I trained it, and I didn't see as much of a convergence I would want to see. Given the fact that we were solving such a simple problem. I mean, I know we are using a very simple neural network, but still the kind of convergence I wanted to see is not something that I did see. There's a reasonable chance I'm doing something wrong, but at least so that is a problem that is currently active in pins. So you can maybe read a couple of papers on it. I think this paper also kind of goes into that problem, is that although this thing works, there are issues regarding its convergence. So you can see that the paper is actually very long. In like what we read was a very small part of the paper, basically because they end up like doing it themselves and stuff like that. Uh, some other random equations. I don't know what these things are. So yeah. But yeah, so that's that. Other than that, I'm just writing this code to test the model out, and I'll just show you the solution that I obtained for the heat equation. So this is the solution. Very simple thing to interpret. Uh, Nothing really that crazy. You can see that at time step equals 0, you have a much higher temperature, which kind of sort of diffuses, and then as and when you increase yourself in time, you start going into these kind of areas. So that means it works. So that's pretty awesome. So yeah, obviously it's not a perfect equation. You can see that it was slightly going into that negative, which is obviously incorrect. But you know what, we can actually do a little bit of training on the video itself, maybe get a better accuracy. We're gonna write a slightly larger model, and then you can train it again. So we're gonna increase the number of layers. So we're gonna make that like 600, and I have to change this to 600. Gonna change this to like a 400, and I'm gonna add one additional layer. So that's gonna be n dot linear, and we're gonna take a 400. Oops. And 400, and we're gonna output a 100, and I'm gonna do a nn dot tan h longer in order to run this, since I'm currently doing it on camera and I already have like recording software running in the background, but that's alright. I'll shut Visual Studio Code down so I can get like, so I'll run this for 150 epochs, and I'm just going to shut VS Code down. That should give me free up a little bit of RAM. Shut this down, and I'll run that now. So we should hopefully get slightly better results. So you can see that this is a really good paper to implement if you are a beginner in this field. And personally, even I found this paper like I have a very hard time implementing papers, and I always end up copy pasting a lot of code when I'm actually implementing the paper. This was the first paper that I really was able to implement by myself. So that's why I would highly recommend for anyone that if you are someone who wants to learn how to code in neural networks and stuff like that, this is a great paper to start out with. So definitely go ahead and try implementing this paper by yourself. This video should be there for guidance, and I obviously have the code up, but as an exercise, I would highly recommend that you kind of go ahead and you implement this kind of for some other equation. A good example, so I'll give you a sort of a homework thing. I'll do it for the Navier-Stokes equation. It's actually a much more complex example, and if you can do that, then I have a feeling that you have kind of grasped the code concept well. I know I sort of rushed through this video, basically like I didn't exactly go into the very depths and stuff like that, majorly because there are very good resources for pins, and I personally feel like I wouldn't be able to do enough justice in terms of the theory and stuff, and so that's why I kind of just gave you the code how that can work, basically because I understand pins to an extent that I can explain it to myself. I don't understand pins to an extent that I can explain it to you guys. So that's why. So yeah, I mean, this apparently is gonna take a little bit of time to run. And you can see, so this is where the convergence issues sort of come in. You'll see that even if we run it, like, this is actually taking way longer than I actually expected it would take. I should have just done it on Google Collab on the thing, but maybe we can get a bit of a processing power boost. Like, I'll wait for a couple of seconds, but if it doesn't, then I'll just stop the video. Alright, you know what, I don't think that's gonna happen. So yeah, so that's it for this video. Pretty much this is what we have ended up with. You can see that we immediately have much better performance. So with the initial model, I was getting this loss 7 point something, and I was getting it at after 100 epochs, and I was actually barely reaching that. Like, in most cases I wasn't even there, I was a little bit higher than that. And the fact that we are still at the 50th epoch and we have reached a loss that's lower than this sort of shows that we were having a slightly less powerful model. And I feel like now we are running with a model that's truly the model that should have been used. So yeah, this is gonna take a little bit of while to execute. It's all, I mean, I'll have the results for this also maybe on the GitHub repository. I'm not sure though. I mean, come on, bro. I literally just changed the number of epochs. You guys can do it by yourself. So, you guys can go ahead and do that. Please do try my kind of homework assignment, whatever you wanna call it, by yourself. If you can do that, that's actually a really, really good thing and a really good practice for you. And I'm pretty sure that you're gonna have a little bit of a ease implementing it. One final kind of an assignment that I'll give you is that you try to actually implement the part 2 of the paper by yourself, and that's like a big assignment, because uh, that is going to be a little bit difficult to do. And so yeah, I mean, I'm not expecting you guys to do it, but if you can, then that will actually be a really, really, really good practice, and that will be a paper that you have implemented yourself completely. I don't know if I'll actually upload any code for that, but if you are trying it out and you want any assistance, then you can reach me out in the comment section and I'll kind of provide something. Okay, actually, we are almost done with the training, so I'll just wait up. I mean, it's just 25 epochs remaining. You can see that we had a brief increase in loss, like we suddenly just bumped up to 8 somewhere around here, which kind of sucked, but we are back to a 5.9 something, so that's a good thing. But you can see that there are certain issues with convergence, because we are literally on this loss for like the last 40 epochs, and there should have been some sort of an early stopping that I should have implemented. But that's alright. So, alright. So you can see that there's this. So around the 80th epoch, around the 87th epoch, we had this increase in loss that I don't exactly know why it occurred even here, but this was much more. This was actually much larger increase in loss. So these are, as you can see, these are the problems with pins. They are not completely researched yet, so these are slightly open problems. So you guys can, if you can figure it out, then that's cool. And let's look at the results. So these are the results. Why are these the results? Because I changed the thermal diffusivity as long as I remember. So you can see that as around 1, everything just hits 0. A good thing that we get from this equation, a really good thing, is that at 1, in terms of time, we do not hit any negative values, we hit 0. So that means it did understand the fact that we can't go below 0. So you can see it's trying to grasp the concept of physics, that how you can't actually go to that particular value. So yeah, that's it for this video, and I hope you enjoyed the video. I hope you enjoyed the solution that we obtained, and I'll see you in another video. Until then, bye bye.